Hey Math Nines, and welcome to topic 7.6. We'll be discussing rotations and rotational symmetry today. Last day we discussed linear symmetry, which is basically if you can take an object, split it down the middle to have two equal halves or two congruent halves to the object. Today we're going to discuss another type of symmetry, which again is dealing now with circular symmetry or rotational symmetry, as it were, when an object can be rotated on itself and still look the same. So a couple of terms to start you with. First of all, what is rotational symmetry? Well, rotational symmetry is if you have an object and you can rotate it around its center, 360 degrees, and if you rotate it over it on its center, and if the object has the same appearance sometime within that rotation, you've got rotational symmetry. So what I mean by that is, let's take a look at our little cross here. Again, these are hand drawn, so they're not perfect. But if I were to take this and rotate it, it's going to look the same roughly when I get to about that 90-degree angle. It's going to look the same when I get to my 180-degree angle. And it's going to look the same when I get to my 270-degree angle until, of course, I rotate it back to its original position. So this object appears the same at 4 different times during its rotation, at 0 degrees, at 90 degrees, at 180 degrees, and 270 degrees. And obviously back when it gets back to 360 would be the start of the rotation again. The last day, at the end of the last video, you may remember that I talked about that this will have a connection with starfish. Starfish are a group of organisms that are called echinoderms. They also have other relatives like sea urchins, and all the echinoderms. If you manage to do a Google search of this, because I did mention you might want to try looking at it. All these animals have one thing in common: they have all rotational symmetry. Most organisms have linear symmetry down the middle. They have line symmetry, but these organisms are actually symmetrical on a rotational aspect. So what I mean by that is that, again, I haven't drawn this perfectly. Here's my little starfish. Again, if you rotate the starfish every essentially about 5 times, right, you're going to have the same look to that starfish as you basically come around. And that object can be shown, or that animal, if you were to rotate it 5 times, it's going to have the same appearance. So it also has what we call rotational symmetry. So that's, I guess, a little nod to the biological kingdom as far as rotational symmetry. But they're the only organisms, only animals that have rotational symmetry. All other organisms pretty much have some form of linear symmetry going on. Okay, so that's rotational symmetry. So if you rotate an object about its center multiple times, you get the same look, or it coincides with the original shape. That's what we call rotational symmetry. And I also mentioned that different objects for different organisms will have different numbers where that number coincides. So I said in this case, on this little cross, that the shape coincides 1, 2, 3, 4 times. That means that this object has an order of rotation equal to 4. So what the order of rotation implies is the number of times that a shape can coincide on itself during the rotation of the 360 degrees. So this, I mentioned, had an order of rotation of 4. So I'm gonna get you to maybe do a little bit of brainstorming right now. Here's my starfish again. Can you tell me what the order of rotation would be for the starfish? How many times does the starfish coincide on itself during that 360 degree rotation? Pause me if you need to. I'm going to give you the answer in 3, 2, 1. The answer is 5. The order of rotation of the starfish is 5 because it coincides on itself 1, 2, 3, 4. Going back to the original, there's my 5th. And now I'm back to my original rotation there. So there's 5 times that starfish will coincide with itself during a 360 degree rotation. Now, based on the order of rotation, we can calculate what the angle of rotational symmetry is. So if you have a different order of rotation, then you also have a different angle of rotational symmetry. So to do this, you take 360 degrees, which is the total amount of the rotation in a single rotation, and you divide it by the order of rotation. So if I wanted to know what the angle of a rotational symmetry is for this this little plus symbol or cross or whatever you want to call it, again, I would need to know its order of rotation. We've already determined the order of rotation on this one is in fact 4. So if I were to take 360 and divide it by 4, I'm going to get an angle of rotational symmetry of 90 degrees, which kind of makes sense because as I turn it, I'm basically turning the object every 90 degrees in order for that object to actually line up with itself. So it's always a 90-degree turn that's involved to get the object to coincide with itself on that rotational symmetry aspect of it. Now, I'm going to give you a question to answer. Here's my starfish again. Here's my lovely little starfish. You now know what the order of rotation is for that starfish. Can you calculate for me the angle of rotational symmetry? Give yourself a couple of seconds to do that. I'm going to give you the answer in 3, 2, 1. Here is the answer. Hopefully you had to pause me. Maybe I have to do some calculations. In order to calculate this one, I'm going to use my order of rotation for my starfish, which we determined was 5. So I'm going to divide 360 by 5, and that's going to give me my answer. Now I got to go into my head right now. I'm having a bit of a slow day today. That's going to be 60 times 5 is going to be 300. And 60 divided by 12 is going to be, 60 divided by 5 is going to be 12. So I'm going to have an answer of 72. 72, I'm going to go with that. I'm going to double check my math on that. Yes, that is in fact correct. 72 times 5 is going to give me 360. Who says you don't need a calculator, folks, even if you're live on TV and you didn't have the answer? Yeah, so it is 72 degrees. So basically what that means is every time I rotate this to get the starfish to coincide with itself, I have to rotate it 72 degrees in order for that starfish to basically coincide with itself as I'm rotating that picture, that diagram, or if it's actually maybe don't rotate a real starfish in real life. They probably don't like that. But if it's a diagram of a starfish, you would have to rotate it 72 degrees every time you want that object to coincide with itself. Basically, what I just talked to you here about on the bottom on the slide was my example of my cross, where we were calculating what the order of rotation was for that, and what the angle of rotational symmetry was. And in fact, I've actually already skipped ahead to the second slide. So if you were wondering where was all this information about the angle of rotational symmetry, it's actually on the second slide. I kind of just jumped ahead because, I felt like it, because that's what you do when you're freewheeling a lesson like I am right now. Hey, so we've done that. So let's go to the bottom of the second page. If you've got your notes up at home, and I'm going to throw up a diagram for you here. I'm going to throw you some pictures up. Now, I wasn't able to draw all of these on the board because, quite frankly, I'm not a good enough artist to do that. But I have drawn at least 3 of the shapes that are on this page. This one, that one, and that one. I've got this one over here, this one here. I've got my really bad attempt to draw the Mercedes logo. You can see that my drawing skills are not going to be up to the challenge of maybe doing that one or the Union Jack over here. If you've got the notes at home, what I'd like you to do is I'd like you to do 2 things with all these objects. I would like you to calculate, first of all, what the order of rotation is for each of the objects. So how many times can you have the object coincide with itself during a 360-degree rotation? And then secondly, based on that information, can you give me the angle of rotational symmetry? If you just want to do these 3 that are on the board here, if you haven't got the notes in front of you, that's great. If you do have the notes in front of you, there are 2 others here that are more complicated. If you can do this one right here, I think you got it made. This one here is probably the toughest one right there. You have to do a little bit of looking at that one to kind of figure out what how many rotations are involved in that one. But maybe just pause me right now, give it a shot, and I'm going to get back to you on it right away, starting now. Okay, so here is the first object. We've got an irregular hexagon. It isn't a regular hexagon. If it was a regular hexagon, we would have multiple orders of rotation going on there. In fact, if we had a regular hexagon, it would be order of rotation of 6, because you'd be able to rotate it 6 times among itself. And we did discuss that a little bit last day when we were discussing equilateral triangles, when we were discussing squares, any kind of irregular polygon. We talked about all the different lines of symmetry. All those lines of symmetry also correspond with the orders of rotation of the object. You can rotate the object, and not just with, they don't just have linear symmetry. They've also got rotational symmetry as well, if they're regular polygons. This has a much longer side on the one side, so we don't have that many. Or we don't have that very. Sorry, we don't have that many orders of rotation. We don't have 6 orders of rotation on this. This really all we can do with it. And again, if you've got your acetate sheet with you, this is where these pieces of acetate can really come in handy. I'm just going to quickly sketch this for you here on my acetate sheet. There it is. There is my little shape there, my little hexagon. So if I flip it like this, is it going to look the same? Nope, it's not looking the same there. What if I do this? Hey, there we go. We got a winner there. So there's at least now 2. We had the original at 0, it looks like itself. And now we have our second spot where it looks like itself. So that would be at 180 degrees. And then at 270, it doesn't look very good. And then we're back to our object. So we know that this has 2 times where the object, this hexagon, looks the same or coincides with itself. So we would say that it has an order of rotation of 2. It's got an order of rotation of 2. Now to calculate its angle of rotational symmetry, I'm going to take that number and divide it into 360, which means that my angle of rotational symmetry for that object is going to be 180 degrees. So that's the first one. The next one, let's do, is the Mercedes-Benz logo. This one here. It is a circle, but inside the circle there is a pattern. If I had a circle, obviously my order of rotational symmetry would be probably infinite because there's just that many possible things in a perfect circle. But I'm going to draw this kind of really rough, and I'm not going to draw the best job of it. It looks more like a peace symbol right now, but you get the idea. There's my Mercedes-Benz logo. So I got it looking like that at 0 degrees. There we go. I'm going to rotate until I get to there. I didn't quite draw this as well as I could have. This is always the problem. I got to redo that one. Hold on, folks. I did not divide that into equal angles. I can tell you that right now. Let's try this again. This is going to look a little bit better. Still not going to be perfect, but we're going to get there. There's my first one where it looks the same. Here's the second one. Doesn't quite look, but you got to bear with me. I drew this by hand, so it's not perfect. That's also a line up there. And then the third one is going to line up like that. Again, I didn't draw this as well as I could have. So I'm going to basically have 3 times where that shape coincides with itself. Pretty much every time that this spike gets up to the top, we have basically a coinciding shape. So we've got 3 times where it coincides. That means it's got an order of rotation of 3. How do I calculate my angle of rotational symmetry? I'm going to take 360 divided by 3, and that's going to give me a value of 120. So my angle of rotational symmetry for the Mercedes-Benz logo is going to be 120 degrees. This last object here that's up on the board, you may have discovered right away that there actually is only one way that you can rotate this and have the object look the same. Obviously, this object has linear symmetry. We obviously know that. We can divide it down the middle and have linear symmetry. But if I try to rotate the object, and again, I'm drawing this very roughly, there's only one aspect where this object looks the same. See, if I go to 180 degrees, they don't look the same. 270 doesn't look the same. There's only one point at which this object has an overlap that looks good. So because of that, it has, we still have to give it an order of rotation. It doesn't have rotational symmetry, but it still has an order of rotation. It has an order of rotation of 1. Because there's only one time during a 360-degree rotation where the object looks like itself. That basically tells us that it doesn't have rotational symmetry, but we can still say that it has an order of rotation of 1 because we can't rotate it on itself and make it look the same. And that basically gives me an angle of rotational symmetry of 360 degrees. If we did the 2 on the bottom here, this first one, this flower, looks, well, it's basically got 8 sides. If you count the little petals, there's 8 petals that have that little indentation on the outside. That would indicate that there would be 8 rotational lineups, which would give me an order of rotation of 8. I'm going to divide 8 into 360, which gives me an angle of rotation of 45 degrees. My Union Jack, basically, it looks, now that Union Jack, well, the Union Jack is basically going to have, it's going to rotate on itself and look the same 4 times. It's going to be very similar to our little cross that we had up earlier. So it's going to have an order of rotation of 4. and then it's going to basically going to have an angle of rotational symmetry. 360 divided by 4 is going to give me rotational symmetry an angle of rotational symmetry of 90 degrees. All right, that's the easy part. Now we're getting into the tougher stuff. Now let's discuss doing a little bit of rotation with some graphing here. All right, so what we've got here is we've got a rectangle. We've got a rectangle A, B, C, and D, or A, B, C, D. And we want to rotate that rectangle 90, 180, 270, all about vertex A. So what does that mean? Well, the point A this is our vertex, which means that we're going to rotate that rectangle around that point. So again, if I've got my piece of transparency, and I'm going to draw this rectangle, it won't be it's going to be the exact same size, but it'll give you the idea. So what we're going to do is we're going to basically take the rectangle, and when we rotate it, we're going to rotate it on that point. So that's what I mean by rotating on vertex A, is that becomes the point of rotation. So there's my 180, and there's my 270. Again, it's not to scale, but this is just going to allow you to visualize what the rotation is going to look like. Here's a 90-degree rotation off of vertex A. Here's a 180 rotation off of vertex A. And there's my 270 off of vertex A. So what I'm going to do is I have to figure out how big the rectangle is. So I can see that I've got a rectangle right now on my Cartesian plane. It's got basically, it's a 2 by 3 in dimension. I've got 3. I'm going from 1 to 4 here, and I'm going from 2 to 4 there on my x-axis. So I know that when I rotate this, when I rotate it 90 degrees, and again, I can use this to help me visualize it. I'm going to rotate it so I know that my 2 side is going to be here. So I know I'm going to have a point there. There's my other point, and I'm going to go 1, 2, 3 to here. And then there's my points there, and then I'm just going to draw my rectangle off to the side there. So there's my first one. That's going to be blue. So blue is going to be my 90-degree rotation on there. That looks good. Now let's take a look at my next one. I'm going to highlight this one green. This is going to be my 180 rotation. So again, now I'm just going to take this and I'm going to rotate it like so. So now this is going to rotate here to that point there, 2. And then I've got 1, and I'm going to go down to 2, minus 2 on my y-axis to there. And then here comes my 180 degree. There's my 180 degree triangle, my 180 degree rectangle, thank you very much. And then my last one is going to be my 270. Again, you can pretty much predict where this one's going to go. It's going to be 3 across, down 2 here. So it's going to go out to here now, because that's 1, 2, 3 across, and 2 down to there. And that's going to go to there. And there is my third rectangle. Now the color coding that I use may not match the notes because I don't have the notes in front of me. Your color coding on your page might be a little different than mine, but bear with me. I mean, my color coding is accurate to what I've got up there. The toughest part of this question is it's asking you to identify all the coordinate points. So now you've actually got to go in and actually figure out what your x and y coordinates are. So for example, A is never going to change. A is always going to be on 4 on the x-axis and 1 on the y-axis. B is going to be 2 and 1 over there. C is going to be 2 and 4. Remember, when you're doing your coordinates on a graph, it's always your x coordinate before your y coordinate. So I'm going 2 to 4 there. This is going to be 4 and 4. So D is going to be 4 and 4. That takes care of that. Now on the pages in the notes, you'll see that I've labeled these. And just so you know, in the notes, I labeled this one is green, this one is red, and this one is blue. So color coordination is not exactly the same as what you see there. But you'll also notice that these have all been labeled with other coordinates. So this is now E, F, G, and then the A stays the same. This is now point H over here. This is point J over here. This is point K over there. And then I've got points M, N, and P. Luckily, A is common to all of them, so I only have to do the A point once. But now I got to figure out what all these other points are. So this is going to be 4 and 3. So this is going to be 4 and 3 for E. This one's going to be 7 and 3 for F. This one's going to be 7 and 1 for G. I'll go over to H now. That's going to be 6 and 1 for H. J is going to be 6 and -2 because now we're negative on the y-axis. This is going to be, K is going to be 4 and -2. M is going to be 4 and -1. I have to think about that for a second. And then N is going to be a 1 and -1. And then the final one is P, which is going to be 1 and 1. So there you go. That pretty much answers the entire question there. That gives you all your coordinate points off the get-go. And again, the rotation was all about, and when it says rotate, in the question it says rotate, it says 90 degrees clockwise about. You'll see that a lot in this unit, about vertex A or vertex B. So when you say you're rotating about, that means that's the point of rotation. That becomes, even though we're not rotating it in the middle of the rectangle, we're rotating it off the corner of the rectangle there. So that's where these questions, you have to pay attention to what point is the point of rotation for these graphing questions that you might see in this unit. All right, let's take a look at our last question for today. So here's the last question. What we're going to do with this one is we've got this essentially pentagon that's been written down. We've got pentagon A, B, C, D, E, and it's on a graph here that we graphed it out. We're going to rotate this pentagon 180 degrees about its E vertex. So we're going to rotate this object 180 degrees about the E vertex, which is right there. If you want, and I would encourage you to try this now, maybe just pause the video, see if you can actually draw this and actually rotate it in relation to that. And I would also like you to try to write down the new coordinates for the transferred pentagon. Now you're going to notice that on the notes, you're going to see the one pentagon, the original pentagon is listed as A, B, C, D, E. And then the new rotated pentagon is going to have the designation A prime, B prime, C prime, D prime, and E prime as indicated by the little notation like so. So you're going to notice that the new pentagon has this designation. This is just a way to designate if you're flipping an object into a new position on a graph, and because they're not the original points, you're basically indicating the new locations on the grid for the corresponding point. So for example, when I rotate this, A prime is probably going to be over here somewhere, and you're going to have to kind of figure out the positions of all those. So anyways, give me a pause for a second. See if you can try to graph this on your own and write down the coordinates for each of the new positions. And these should actually be A prime, B prime, C prime, D prime, and E prime. I'll also go through the coordinates of A, B, C, D, and E with you as well, just to kind of get all the coordinates on, because it's good practice to see if you can get those coordinates. Anyways, pause me right now, see what you can do, and we'll be at it right. Boy, choking on my own words, but here we go. This is how we're going to do it. So we know that the rotation is going to be about vertex E. Now I'm going to just draw this on a small scale. It won't perfectly match. But we're doing a 180 degree rotation to this object. So we know that it's going to look like this when we're done. We know that. The point is, where are we rotating the object? Well, it's saying to me that we're going to rotate the object at this point here, vertex E, which means that if this is vertex E, I am basically going to rotate the object around that point. So I'm going to get obviously a larger version of what I've drawn here, but that's basically the E point is going to be the connecting point between the two objects. Okay, so I now know that this side here, which is it's going to be 1, 2, 3 in length. I need to make this 3 in length up to 7. So that's going to go up to here. And that essentially, and again, what I can also do with these transparency sheets is this. I can write all my letters down to figure out where they're going when I rotate the object. right? So here's my letters, A, B, C, D, and E. When I flip it like so, I now know that this point up here is going to be D prime. I know D prime is going to relate to that point down there. So I'm going to basically draw this to there. That becomes this side over here. Now, this side here needs to go down. So I know that it's going to go one lower. And this position here looks like it's about 1.5 because this is a width of 3. So the A is going to be 1.5 in the middle of that point right there, roughly there. So I need to move this over 1.5. So I'm going to go down 1 because this is up 1. I'm going to go to 1.5, which is here, and I'm going to go to 3. And my point's going to be roughly there. So that's going to go right down to there. This becomes point A prime. So that's that point right there. I know that D connects across 3 over to C. So I'm going to go 3 over from 5. 1, 2, 3 is 8. And we're going to be on 7 over here. So I'm going to go 8 and 7, which is roughly there. A little tougher when you don't have actually grid paper, but I'm trying to eyeball it as best I can. That is going to be C prime over there. I know that this is going to go down 3 because the side length of that the side length here is 3. So I'm going to go back down to 4, and it's going to be 4 and 8 now. Something like that. And then my last point I can connect in like so. And there becomes my points on the graph. Now you can see that in the notes it's showing it to you there, and it's also showing you the orientation of the actual points. You could argue that point is point E prime, but because it's actually sharing that point with E, you could argue that that point is actually still point E because you're sharing the original point E. All the other ones are new designated points, so we would call this A prime, B prime, C prime, D prime. E prime, you might have to call it E prime, but you could pretty much say that it's point E because it hasn't moved, because E is the point of the rotation of the object. The question now becomes, what are all the coordinates? Now I'm not going to look at that because my coordinates are listed on the page right now when I click the button, but let me just quickly run through the points. I know that D is going to be 5 and 1. I know that C is going to be 2 and 1. Again, remember, you're always doing your X coordinate before your Y coordinate. I've got B is 2 and 4. I've got E and E prime as 5 and 4. So that's for both of them because it's this. I'll put it on both sides just so that you can see that. 5.4 for E and 5.4 for E prime. Again, that's the vertex. That's where we're rotating the object. That's the term vertex that we're using there. A is a difficult one because we're halfway between 3 and 4. So it's going to be 3.5 as the X coordinate, and it's going to be 5 as the Y coordinate. So that's going to be 3.5 and 5. Now I'm going to do the rest of them. I've got A as 6.5 and 3 on the Y axis. I've got B as 8 and 4. I've got C as 8 and 7. I've got D as 5 and 7. And I think that covers them all. And I think that is right. I'm looking at my notes. They all look good. So that's basically the answer to that question. Actually not too shabby, but that's the kind of graphing questions you could see potentially with kind of this rotational, these rotational questions that you might see later on a quiz or an exam coming up later in the unit. That's it for this topic. Before you head out, if you're still having issues with rotation or rotational symmetry, give that video a watch. It might help you out a little bit more in case I somehow manage to mess things up like I'm bound to do occasionally in these videos. Homework, well, it's right there, and it's right there. It's everywhere. Here's your homework for tonight. You got questions 4, 5, 6, 7A, 9, 12, and 13. You're going to complete those on pages 365 to 367 in the Math Makes Sense 9 textbook. That's it, folks. And you know what? The good thing about the next video is it is, in fact, the last video for this unit. We're going to be covering 7.7 next time, which is identifying types of symmetry on Cartesian planes, which is basically a fancy way of doing more of what we're doing here with our graphing. Cartesian plane, just a fancy word for graph. So won't you join me for more graphing? Bring your graph paper next day, because if you haven't got it already, I don't know what you're doing in this unit. And I hope to see you very soon.